How are you guys doing today? You may have noticed I'm becoming a movie star. Chadi is from AUB IT. He is helping with recording the sessions. We're going to try and record them for the rest of the semester in case some of you are not able to make it or some of you are sleeping in the back. Then you can watch it later. So we'll see. Hopefully we won't need to have many of these recorded, but we'll try to record them as long as Shadi is available. They're not always available. I think there's been a lot of emails since we last met. We were supposed to have an exam on Saturday, and by now everyone knows that we haven't. And I've done a lot of effort to try and make sure everything is balanced. Some of you, or at least a couple of you, asked me, how do I evaluate myself? They were interested in seeing how well do they understand the material we've covered to see actually, where they stand. And a good way to check is to actually go through the practice problems without looking at the solution. The practice problems could have been a very nice comprehensive take-home exam to check, how much you guys know. So if you want to find out how well you know, go through the practice problems without looking at the solution, then look at the solution and see actually what you understand and what you do not understand. And if you have any questions, make sure you reach out to me or the TAs and ask. Okay? Now, in terms of assessment going forward, I am not making an assumption that I will do the midterm. Instead, as you guys saw, I am redistributing the load of the grade in terms of everything else. So graduate students will have the wonderful opportunity to actually work harder on the project and use that to a higher percentage. Undergraduate students will have the option to work harder on the extensive assignment, the Hamal assignment. I will be assigning more. I actually did not do this weekend, although I could have. I just wanted to, give you guys a little bit of breather, because I know a lot of you had, several exams over the weekend and Friday and what have you. And some of you, actually all of them got pushed, except there was some exceptions. People decided just to keep them. So anyways, it was just a breather to reset and just see where things are at. So now I consider we've hit the reset button to refocus and just get through the end of the semester. There will be at least 2 more data camp smaller assignments, not full course, but chapters, of course, primarily on unsupervised learning, and at least one that actually have you practice. If you have a competition or a project that you want to work on, how would you approach this? So basically, think of it this way. The different data camp assignments were focused on, not all the time, but mostly on particular areas. This is kind of an umbrella. One of them is an umbrella. And I have a couple that I may assign. One of them works with Kaggle competition. Anyone is familiar with Kaggle competitions? A few of you. They are, a source of a lot of competitions with large data sets. Netflix was famous to use Kaggle. So it will actually, if you guys got interested in doing competitions, these data camp assignments will also, help you in competitions. What else I want to say? There may be opportunity to give more data camp assignments, possibly for bonus work. I have to still think about this. It's a delicate period where I want to make sure, I don't move the percentage from the midterm to other things because it was creating anxiety, and now give you a lot of work in a few weeks and then create another kind of anxiety. I think we have covered a lot of material, and you guys know now we have even 2 weeks extension to the semester. If we need them, I believe we will definitely use the first week they've extended. I'm not sure if we will need the second week, but I think we have a lot of material we covered, and I want to make sure that there are certain things that, here and there that I've not covered, I want to get through before the end of the semester. But anyways, I want to pause and see if you guys have any questions with all this resets that we've been doing, all the distribution. I had questions about data camp, old assignments. There are some people actually who did not do the previous data camp assignments. I encourage everyone to finish them. I will not penalize to zero those who did not, given that, this resetting, they become even more important. So I will allow those who did not finish it to finish it with some penalty. I don't know what that is, but it's, it's not going to be detrimental. I still think, it's important to reflect that we've learned stuff. So anyone who has not done previous data camp, go ahead and finish them and make sure you finish them as soon as possible. At this point, I have not set, I will, when I post new data camp assignments, I will set deadlines. So I will say, let's say the next data camp will be from a week from today. The goal is not really to check whether you finished it and penalize you, but just to give you a way of regulating your load. So until further notice, all deadlines between now and the end of the semester are flexible deadlines. So if I give you a data camp assignment, you could submit it within a week or choose to submit it within 10 days, as long as you finish all of them before the end of the semester. I urge you and will urge you, assuming our brains can function semi-normally, that we finish them on time per the schedules. But if you have to happen, some special situations, the flexibility is there. Yes, Wafi?
First, thank you for your flexibility for your procedure. Second, I wanted to know regarding, do you have a tentative date for the final or not yet?
The final will be scheduled with the help of the registrar. I don't know what that date is. You guys have seen the schedule goes all the way till December 29, I think. I know that all of us would prefer to finish by December 15. We may have an opportunity to, let's see how the next week or two go. We may have an opportunity to schedule it ourselves, but the problem with scheduling it ourselves, a particular date, and we've seen this before, we have about 90 plus students in here, so conflicts will start going crazy. And that's why, using the registrar will help making sure there are no conflicts. So the default is that the registrar will set it.
And as a follow-up, so definitely to have 90 students agree it's difficult, but is there a possibility to have two finals, one for the graduate students and one for the undergrad?
There may be some questions that are different, but it's just one final.
It's one final.
I mean, the timing is the same. You're thinking, have different timing for the graduate students? Get out early. No, it's going to be a heavy final. Let me say this. It will be a heavy final, and there will be, if I do add, which I don't think I will, if I do add a question, it's possible, but I don't think I will.
As for the lecture on the non-linear SVM, we didn't take a session for it, a separate session for the non-linear SVM.
We did not?
We did not take a session separately just for slides that you put on Moodle, most of them we didn't go through.
I'm sure I did. Maybe I went in the other section, maybe not in this one.
في كتير كمان من غير colleagues كانوا عم بيحكوا عن ذات الconcern.
No problem. I can bring it back to focus and talk about it. But just to briefly answer, and I thought I covered it here, but maybe it was in the other section. The way we go about from linear to nonlinear is basically we start from where we left off with a linear formulation that says everything is in terms of products of vectors. And so if you go to higher dimensional space, you want to take the linear and assume you have more terms that reflect the higher order polynomials. So it becomes equivalent to a mapping from the lower dimensional space to a higher dimensional space. Let's assume this mapping, we call it phi. So the product that I used to have in lower dimensional space as linear still stays linear, but now it's a linear product of the two mappings, right? Phi transpose. And up to here, everything looks like the linear. And then the way we jump, even though it's nonlinear, right? So we said, assume I know the order of the polynomial. It looks like a product of linear terms, but now multiplying higher order terms, right? And the way we jump from dealing with this unknown higher order term, we say this product of vectors that now is a mapping of higher order polynomials can be equivalently represented by a kernel of the original space. So I replace the product of the two phi vectors with a kernel that's in terms of the original vectors. And those kernels, there are a finite set of choice, and that's it. This is the end of it in terms of our discussion. So now everything, what we have, whatever you have a product in your equations becomes, in linear, it's still a product. In nonlinear, it's a kernel of the two, whatever that expression is. Okay? I thought I covered it here, but if you guys want, I can, bring it back, just talk about those slides and make sure it's covered. How many of you want me to bring it back and discuss it again? Why not, right? It's free. Okay. كل شيء ببلاش كتر منه. Okay, so next time. Any other questions? I mean, please bring up things like this. So sometimes between this section and the other section, I may be covering things, one way or the other, there but not here, or here and not there. And I go and post the slides thinking I covered it in both places. So if you see something on the slides that's either not clear or I did not cover, just bring it up to my attention. So any other questions? We're all good? Okay. Lights. Still okay? All right, so we're still in unsupervised learning mode. And today we talk about something interesting that has multiple kinds of applications, and that's taking a higher dimensional space and reduce it. And reduce it through a particular method that's called principal component analysis. Now this discussion is still unsupervised. Anything where I discuss, remember, the x values or the attributes without reference to the y values or the labels is unsupervised. So this will fall within that realm. So I will talk first why we want to do dimensionality reduction, and I'll use compression and visualization as two motivating examples. Then I'll talk about the formulation of this dimensionality reduction and how PCA plays into this. Then magically I'll show you the algorithm for PCA. I'll give you some intuition how it comes about, but I will not prove that this algorithm actually satisfies the original objective. I'll give you a couple of perspectives on PCA that are pretty cool to know. And then once we know how to use it, I'll talk about also how to reconstruct the data from compressed. And then finally, we've talked about this way back, and we use unsupervised as a step in supervised. Well, we'll see one excellent usages of PCA as a step for supervised, and we'll see places where it's not a good idea to use PCA for supervised. How many of you are familiar with PCA? كل ما طولت كل ما بيطلعوا الايدين. Okay, there's few hands. Okay, fine. So I'll assume no one has seen it before. So let's talk about motivation. Let's assume, I have a lot of data, a lot of features, and, when I have a lot of features, it may be good, it may be bad. What are some good things about having a lot of features? What are some bad things about having a lot of features?
It can be overfitting if you have a lot of features.
If I have a lot of features, I could be overfitting.
Bad thing is you could run out of memory.
You could have a lot of space requirements.
It won't be focused. It won't be focused.
It won't be focused.
It would be harder to draw the pattern.
Path in the learning, a pattern. It's harder to, okay. Maybe, yeah. It definitely will be harder, definitely, to draw a pattern.
High sensitivity model.
Sorry?
The model sensitivity, the model has high sensitivity.
In terms of kind of overfitting type of thing. So this is true. Performance, let me just get through one more thing that says harder. Performance, when I'm trying to process things with a lot of data, both memory are an issue, performance are an issue, plus, the other thing we said. So I could have actually, a lot of features, by the way, could be good and bad. So that's why, so if you don't have enough features or features that you really need are useful, then you're going to have a bad model. If you have a lot of features and they're noisy features, you're also going to have a bad model. So, choosing features is important. So let's take this example and let's look at this data. If you guys look at this data, this is in 2 dimensions. And obviously, if I want to represent these points, they're originally in a 2-dimensional space. But the question is, can I somehow simplify this representation without really using a lot of information? Carl?
Yes, because whether the sizes in centimeters or inch is probably the same. It's just
Yeah, very good observation. Even if I hid those, yeah, very good observation. Inch and centimeter are actually linear. So these samples, maybe people didn't take the exact measurements and they were slightly off, but they're really linear. So this is almost a line, right? So even if I hid those and I give you this, you'll see that there seems to be a linear relationship between them. So in this linear relationship, all of those are sitting on one axis, right? So if I take any of those points, there are 2 ways of representing it. One is in terms of x1, x2, and the other one, if I draw this line, let's call that dimension z, so my axis now is z, I can refer these points with respect to z, not with respect to x1 and x2. And if I refer them with respect to z, how many values do I need to represent those points? 1 point. So this is kind of a cool way, actually, of going from 2 dimensions to one dimension, and roughly, in this particular case, not losing much, right? So all of these now become projected on the C. So if I just take this Z and lay it down, this becomes all the points on the Z-axis. So this one is over here, and so on. And the way I go from here to here is just simply by projecting those on that line. Orthogonal projection to that line. And so x1 becomes z1, and so on, okay? The same story could happen, again, as another motivation, from 3D to 2D. If I look at this, three-dimensional set of data points, as initial look at this, it seems like this is all over the place. I don't see that kind of linear relationship where things are squeezed into one place. But if I rotate this a little bit, let me show you what I see. If I rotate it, I see that these things seem to somehow fall in a different shape. And if I fit them on a plane, they seem to all fit on that plane with two-dimensional axes now, Z1 and Z2. So the story is the same like we had before. Instead of looking at this in three-dimensional space in terms of x1, x2, x3, if I take a plane that's along this direction, I can project all these points on this plane and almost not losing anything, and I get a two-dimensional plane. And this two-dimensional plane now, the x and y axis are not x1, x2, x3, but there are this new axis that are z1 and z2 that we have come up with to give us our plane. And the goal of PCA is actually to try and give us those vectors or directions z1 and z2.
Okay, so putting this effort to reduce the order from 3D to 2D and doing this transformation, can I have this effort much more painful than the effort of having the three-dimensional domain?
One more time.
Okay. Can the effort of transforming this 3D into a 2D problem be more or bigger than the effort of having the 3D initially? I'm putting effort to transform it from 3D to 2D.
That's right. So you're saying in terms of performance.
Maybe it's not a trade. It's not a good trade
for performance.
Yes.
Yeah, for performance for sure. If I just want the data alone, any work you do on it is more work. So it depends. So if we're trying to do find patterns, if somehow I can tell you this data is actually just along one direction, isn't that a wonderful pattern to know?
Yes.
So the PCA, think of the PCA as a method to understand the data. So if you don't want to understand it, forget about it. But if you want to understand it, it's useful.
Okay, so we should have a criteria: one to use PCA, and one to consider that that it has a big trade-off and not use it.
Sure. And one of the biggest use of PCA is we're working things backward. But if you want to do dimensionality deduction, and if you can do dimensionality deduction, it would be wonderful, right? Because now, if I assume that my next step is try to understand this data, then it's easier to work with this than to work with that. Okay, here's another motivation example. Hopefully, by the time I go through this, you're even more convinced. Let's say I have, n-dimensional data, 50 dimensions, 1,000 dimensions, and I have, different samples for this data. And it would be good to try and understand, how does this data look like? If I were to look at it in some dimensional space, can I somehow get some semantic understanding of those? And it will be difficult, to say the least. I actually argue it's impossible to visualize all of these in one shot. You can say I'm going to visualize those three together and so on. You can do subsamples of those, but you're not going to be able to visualize all of them. So it would be very cool if I had a way to visualize them. And one cool way to do it is actually to have a reduction of space from all of these into either two-dimensional space or maybe three-dimensional space in the worst case. And now I can look at these data points and I can see how these are spread over here. And if this new space, Z1 and Z2, somehow carries a lot of information or the most important information about that higher dimensional space, I can look at this and make sense of it and say, well, these two, I can do clustering on this and say these countries seem to be closer together. So if I do my analysis on higher dimensional space and I say, did I do a good job? You could try to visualize it and see in two-dimensional space, do my results actually seem to make sense? And so this is one very common use also of dimensionality reduction, whether we're doing it through PCA or something else that you guys will have on your assignment called TSNE. So this will be on one of the data camp assignments, and it's even a better way of doing dimensionality reduction for visualization. But you know, this is pretty cool. How many of you have worked on natural language processing or trying to do something with natural language processing? One person at least, right? So imagine, again, those of you who worked in natural language processing, you know that when you want to represent words in terms of features, that representation typically is a very, in its raw form, it's very long, right? It's 100,000 long features. And if you want to deal with, you know, visualization of what's going on in that space of 100,000, forget it. And so what people do, they say, let me try to come up with a better representation, and they go into things like in the world of neural network called embeddings, which take it from 100,000 maybe to 1,000. Still 1,000 is still not viewable. And then you say, now let me take the 1,000 and bring it down to two-dimensional for visualization. And so they look at these, if you've seen maps of words in three-dimensional spaces, بحطوا dots, and they say this is the word love, this is the word like, and in that three-dimensional space of semantics, the word love and like are close to each other. The way they come up with this is by following mechanism like this, so that you go from 100,000 ultimately to just two-dimensional, and that starts giving you some way of, you know, building intuition of what's going on. So very powerful, very useful when you're doing your analysis to try to bring your data into a lower dimensional space that actually you can visualize it. Not always correct, but you know, it's just another tool to see, are things making sense? Okay? Questions so far? So this is our motivation. Basically, we want to find a method to do dimensionality reduction, and that takes us into PCA. So what does PCA do? Some of it may sound familiar. What PCA will do for two-dimensional data is take two-dimensional data, like I have here, and bring it down to one dimension by finding that one line that is closest to these points. So, do you remember that discussion about support vector machine? What is the line that gives me the best separation between regions? Well, this is not support vector machine, but you know, it's again looking at what is the one thing that optimizes something, some objective. And here, what is the one line? If I take the red line, the blue line, and the green line, which one of them is closest to the points? Well, everyone is saying the red one because if let me just compare the red and the blue. How do I find the distance to the red? I project each point orthogonally to the red. I add up those distances. That's the distance to the red. If I do the same for the blue, I add up those dotted orange lines that are projections or distances for each point to the blue line. I add up those distances, and that's the distance of that blue line to the points. Which one is the furthest away from all of them? The blue one, the orthogonal one, right? The kind of thing, right? And so the green is kind of closer and the red is the closest. So what we want actually is to, of all possible lines, find the one that gives me the minimum distance between the original data points and the approximated data points. So these would be the approximated data points on the slide. Okay? Questions? The same thing would apply for 3D. So in 2D, the way we want to formulate it for PCA is find me the direction of that line. How do I specify the direction of a line? Through a vector. Find the vector, and typically we look for a normal vector, which means, of unitary value, which is equal magnitude 1, and then would be orthogonal to other vectors that we may find. But in 2D, there's only one of them. So we want to find a vector u that represents this. So u could be this way or that way. It doesn't matter. Either way, that will give me the same line. So I could have a u in this direction or a u in that direction. That would be fine. If I have 3D and when I find 2D, then it will be find not just one vector, but k vectors. In 3D to 2D, it would be 2 vectors. ND to KD, it would be k vectors. So find the k vectors of all possible vectors whose distances from the points are minimal. And so now we have, and distances is represented by this projection error. Okay? So now we have a mechanism to know what we want, and now we're ready to actually get to the algorithm. So, this would be, in this case, U1 and U2. Before I talk about the algorithm, I think I shared this before, and I'm going to remind you of the story. I had one student who has taken data mining with me a few years ago, 4 or 5 years ago, and that person was doing the master's as a non-thesis. So under a non-thesis option, for those of you undergraduate or even master's, I'm not sure if you know this, as a non-thesis option, students do not have to do a master thesis, but they do have at the end an exam that they have to take in a list of courses they declare as their core areas of focus. And so it's an oral exam. We just come in and start asking just general questions to see how well they understand. And so one of the questions I was asking, I gave a picture like this with points on it. Poor guy. I mean, the guy, smart guy, he's working full time, hasn't looked at the stuff in 4 or 5 years. Just came thinking, okay, it's going to be just, I'll remember everything. So I gave him what I thought was something simple. I said, can you show me the line that will help me in doing regression on this, right? All of you, trivial question, right? Remember the story I told you? What did the guy do?
The classification one.
He drew me this line. Let me just draw it again with another pen so you guys see what. He drew me this line. So, شو صار؟ ايه جرس رايت بهدلنا كيف انا على اساس انا معلم الكورس وفي اساتذه باقي انه مش بس فضيحه له فضيحه لإلي كمان انه معقوله هذا يكون regression. So what did he do in his mind?
Classification.
عمل classification مع انه there's no classification here, right? So now, to add to this possible confusion, we have, so صار في عندنا 3 possible lines we could see this is linear regression. Maybe. This is classification, maybe. And now there's a third line. I'm going to use dotted here. And this is PCA reduction, maybe. So I'm going to make the question a bit more difficult on you guys. Which one of these are valid maybes and which ones are not valid maybes?
Regarding what?
Let me give you a little bit more data. This is X and Y. X as data and Y as labels.
So ما في classification. You have no classification. ما في PCA.
So حدا يرفع ايده ويقول لي ليش؟ كارل؟ Oh, حدا كارل already said that. ذاكرين اسمك؟ آية.
Because PCA needs unsupervised learning and هون حاطين labels lines.
So Y automatically says supervised, this is, as labels versus X. So, and given that we're showing these points as Y versus X, this is a numerical problem, right? So classification is not valid and PCA is not valid. This can only be regression. If I tell you this is X1, X2,
Regression is not valid.
regression is not valid, right? Could this be PCA? Could I have a PCA line over here? Yes, we can. This is exactly what we've been doing, right? It's unsupervised, looking at this pattern. Can this be classification? Can this line be classification? Yes, if I have labels for all these points, right? Which would be something that we're not showing out of this board, right? So this maybe these would have to be somehow labeled differently to reflect that the ones above are different than the ones below. Okay, clear?
If there were no labels, this classification line would be some sort of clustering line.
There you go. So we could talk about clustering and say this is a group, this is a group. If it's what, yeah, it wouldn't be classification though. There's no. With clustering, ما حكينا online. We talk about groups, right? Okay. So I assume you guys get the story. So this is, oops. Putting a line here would be regression. Putting a line here would be PCA. So one difference we talked about is the Y in X versus X1, X2. Another difference, and also very important to know, when we compute the objective function, the error function, what are we trying to minimize for regression? Difference between?
Rejections and actual value.
The model output will actual value.
Which is what?
The
On the figure, what is that?
The vertical distance.
The vertical distance between Y and the line. The Y values, which are those points, and the lines, that vertical distance. Over there,
Perpendicular.
the perpendicular between the points
And the line.
and the lines. Okay, very good. This is same story saying, PCA is not regression, also in higher dimensional. All right. That beautiful algorithm that actually works out is called principal component analysis. And before I talk about this, I added a couple slides to cover a little bit of linear algebra for those of you who may not have seen this before. Singular value decomposition. How many of you have seen it? Some of you have. Okay, so singular value decomposition is a decomposition into taking a matrix and decomposing it into 3 matrices with certain properties. They will have, if the matrix actually is not square, they will have different shapes. One is m by k, the other one is k by n. Notice m by n is a dimension, so there's a k in the middle. And that middle matrix is a diagonal matrix that has only values here, but then zeros above. Now, what we care to know actually is that for our purposes, we're going to use singular value decomposition when x is symmetric. When x is symmetric, this will have the same shape as this. Sorry, not symmetric, square, I mean. This will have the same shape as that, and all of these will have similar dimensions. And this actually becomes the transpose of the one on the left. So for us, what we care about to know about SVD is that it's an alternative way of finding eigenvectors and eigenvalues. How many of you know? Hi, everybody, I hope. Eigenvalue, eigenvector decomposition. So SVD is an alternative way of finding eigenvalue, eigenvector. Hal S matrix, that's in the middle, gives me the eigenvalues. This matrix here, the columns, gives me the eigenvectors. And the first column is the first eigenvector corresponding to the first eigenvalue. The second column is the second eigenvector corresponding to the second eigenvalue, and so on. One more thing about, obviously, as long as you have this corresponds to the right one, you can have any order you want in here, as long as they correspond. But typically, and for many reasons, we try to sort this. So from largest eigenvalue to smallest eigenvalue. So those eigenvectors actually, the first one corresponds to the largest eigenvalue, the next one corresponds to the next one, and so on. Okay, so their order usually is a reflection of the strength of the eigenvalues. Okay, so let's see what else I have. So SVD is an alternative to eigenvalue. It provides factorization. It contains eigenvectors of x. U itself, it becomes orthonormal. So if I do U transpose, what's orthonormal? Means if you take the rows or vectors and multiply them with each other, if you multiply the vector with itself, you get 1. If you multiply the vector with something else, you get 0. So think of like the x and y axis. If you had to have the ij basis vectors tabolon, what's the norm of I? 1. The norm of j? 1. The product of I with j? 0. The product of I with itself? 1. Okay, so this is exactly how these vectors behave. Okay? S is a diagonal, and so on. We talked about this. And if it's square and real, V would be U transpose. And the vectors can be thought of as the basis functions. So, apologize for my animation, but this is how the algorithm, PCA algorithm works. So we're done with the background on SVD. So I just wanted to let you know what SVD is. Basically, as far as you're concerned, it's a way of finding eigenvalue and eigenvectors. So if we're given a training set, x1 through xm, m is the number of samples. So m samples. I construct the covariance matrix X with itself in a way. So X transpose. Another way of doing it is doing, sorry, قبل ما أحكي عن covariance matrix, I have to scale things. So before I do my covariance matrix, I have to pre-process the data. The pre-processing of the data making sure I scale. So عندي matrix that actually will be X with itself. So before I take all the vectors X and I scale them. So just to make sure all the features are in the same scale.
Why don't
Why? Because remember, what we are ultimately doing بعدين is taking the space and then reducing it. So if some of the features are large compared to others, they're going to play a more significant role. So I want to make sure I neutralize the effect of the values. And just to think of an example again, comparing two people based on age and salary. You do not want to compare based on the absolute value. You want to compare based on a normalized value.
Why don't we normalize?
But that's what we're going to do. That's exactly what we want to do. So we take the x values, we normalize them. So long story short, I take the mean, and then I subtract each value from its mean and divide by either the max range or the standard deviation. So I take each column and I do this process. Exactly. And then I compute my covariance matrix, which is the product of the samples with their transpose. So each one of these product is what? A scalar, a vector, or a matrix, and what dimensions? A scalar would be 1 by 1. What's the dimension of xi? N by 1. Now it's the number of features placed as a vector. So this is n by 1. 1 by n, I get n by n, right? So this is, and if I do this for all of them, add them up and average, I get the covariance matrix represented by sigma. And now I take this covariance matrix, and be very careful here. This covariance matrix is after removing the means, much more important than the scaling. Otherwise, it won't give me the effect. The scaling is definitely needed if things are wacky, but if things are not, large or small, scaling may not be needed. But the subtraction from the mean, absolutely. So once I have this covariance matrix, I just do my singular value decomposition. I find my eigenvalue, eigenvector decomposition, and the columns now gives me the vectors that I care about, and I can project my old data using whichever number of vectors I want. So if I want to project from n dimensions to just one dimension, I just use u1. If I want to project onto 2 dimensions, I use u1 and u2. And how do I do that projection? I'll clean up the slide later. But how do I do the projection? Basically, I take those columns that I picked, I take their transpose, and every vector is dot product with the new x value to give me the projection. Very similar to the way you guys do x1, x2, right? If this is x1, this is x2, this is I, and this is j. The basis. Can you guys see? Well, do I need to turn the lights on? So if I have, camera can see also? Well, okay. So if I have ij, and I have a vector u, how do I find the x value of u? It's u dot I, right? خليني نسميه something else لأنه مسمين هون u. So w. So wi will give me the x1 value. W dot j will give me the x2 value. Or vice versa, I dot w with j dot w will give me the x1, x2 values. And w has to be n by 1. Yeah. So I here would be I transpose 1, 0. With J would be transpose 0, 1, right? So 1, 0 times the elements of W, x1, x2 will project the x1, with J as the vector 0, 1, transpose times this will give me x2, right? So if I generalize this concept, instead of having i's and j's, I take a new dimensional space وعنده u1 u2 as its basis. How do I find projections onto u1 and u2 vector space? I take whatever vector I have, w, right? And I do the same thing I did there. I take u1 transpose w will give me the projection on u1. u2 transpose w will give me the projection on the other axis. So this is exactly what we're doing here. We're taking the eigenvectors, which represent the different bases of this new space. Each one row of them is one of those u vectors. Transpose an x coordinate or a w sample, I get the projection onto the new space Z. What's the dimension of this reduced U? If we pick the k vectors, what's the dimension of U? The reduced one would be n by k. Transpose becomes k by n. X itself is n by 1, k by n, n by 1, I get k by 1, the reduced dimension. Sounds good? Now, let me give you not the mathematical proof, but some intuitive understanding what's going on here. Why is it that, we're doing this covariance and then we're picking vectors that have high eigenvalues to be the most important? While when I started the problem formulation, I told you I want to find, of all possible lines, the one that gives me the smallest distance to the points. So if you go back to that 2D to 1D, why would the eigenvector that I want be one of those? Anyone who knows, PCA may actually have a chance of answering this. What is another interpretation of PCA? What does PCA do? What are the vectors the eigenvector that PCA produces, what do they mean? Ala, what do they mean? Sorry? Yeah, they're orthonormal basis, كلنا استوعبنا orthonormal basis, but there he said something else. It's the basis where there's more information. What does that mean? Let me go back to some of these. Let me go back to this. What does it mean that there's, which line has the most information about the data points? Why not the orthogonal one? Well, one way of interpreting this, the interesting information is not when the data is the same. The interesting information is when the data is different. So if you can find the axis where the data varies the most, that's the axis that has the most information. So if you look at those points, how do they vary? Do they vary in the x1 direction or x2 direction? How do they seem to be spread?
In both.
Both. If I were to tell you of all possible lines in the space, which line are they spreading the most on that line? It's this same line that we've been talking about. This is where they spread the most. Where else do they spread? They spread orthogonal to this. But orthogonal to this, the spread is small. And on that line, the spread is large. So what really this PCA is doing, it's actually finding me the vectors. بيطلع بالكاميرا بعد. So it's finding me the axis where the spread is larger. And that spread is actually being reflected by those eigenvalues يلي هن أصلا came from the covariance. So when I look at the X with X transpose, it is trying to find X and all the other X's, how are they similar or not similar? So by looking at this one that actually has the highest eigenvalue, it's reflecting the ones where the spread is the most. So another way, intuitive way to think about which axis do I want to find, if I give you guys can now start build intuition into this. If I give you data like this, where's the data spreading the most? In this direction, right? This will be your direction of your first vector. Where is it next? In this orthogonal. And those two together comprehend everything. This is the orthonormal base, right? So you're going to have the next one orthonormal to it, orthogonal to it. So this is the beauty of this, PCA understanding that you could look at it from two different perspectives. One perspective, it's really finding us the line or those lines one after the other that minimize the projections, or vice versa, looking at the ones that actually most represents the variation. And we'll see actually even when we're trying to pick those components, people use the term variation because that's exactly what it's trying to do. So in short, when we go back to this algorithm, we're going to find our eigenvalues and eigenvectors. And the first one corresponds to the highest eigenvalue, which is the most important. And then the next one will be the next most important. And the third one will be the next most important. Each one of them capturing variation in the data. And variation is information. You guys know what information in the probabilistic sense mean? Log of, right? P log P, right? Probability of log. I'm going to digress for a second. We will talk about information when we talk about feature reduction. But since Ala brought it up, I want to use it also to reflect why variation is important information. If I want to transmit one bit of data, 0 or 1, actually I already gave the answer, but let's just say I want to transmit 0 or 1. And I want to send this over the line, and some Ala on the other side, he has his phone, and he's going to receive my transmission. How many bits do I need to represent 0 or 1? Everybody says? How many? 1. Are you guys sure? Any other answer?
1.2 says to represent each bit like 4 bits, so that you lose 2, you gain 2.
لا هيك وسخت أكتر. One actually is already the worst that we could have. We could do better. We could do better than 1.
No bit.
I could do no bit. If I could do no bit, can I transmit 0 or 1 to Ala somehow without any bits?
If I don't transmit, then it's 0. If I transmit,
لا, if I transmit, I'm transmitting, I will transmit, but with, but I will not, I transmit with 0 bits, basically I don't transmit. But how do I do this?
If there is no change, I guess.
If the answer is already known, right? if Allah knows that I'm going to send them 1 all the time, there's no need to put any bits in it. If there is no unknown in the data, there's no need for bits. But the more variation I have, the more interesting things come, the more bits I need. And actually, the highest you need for one piece of information, if it's a binary type of information, is 1 bit. The more you know about one side or the other, you can even reduce that on the average. And the way you can compute this, actually, those who know the equation for information, it's the summation of minus p log p. So if the probability of both 0 and 1 are equal to half, and you do the summation of p log p, the answer will be 1. Sorry? And if the one of them is 1, p log p واحدة بتكون 1 log 1 والتانية بتكون 0 log 0, right? Which, it's going to be 0 in both cases. So, and if it's somewhere in between, and that takes me to, the extension, the same thing goes if I have, 2 or 3 varying things. The more information I have, the more interesting things become. So this is actually when an information is related to variation. The more variation, the more information. And so when Allah said information, this is why information, is variation. All right. How are we doing on time? Are we 8 minutes? Okay. So clear? This is it. So just to summarize, the algorithm from what you guys need to know to do PCA is extremely simple. You take the attributes X that don't have labels. You subtract the means. You scale. If you have to, if they're all in the same range, you don't have to scale. But if they're not, if you want to be on the safe side, you can just scale anyways. You scale. You do the covariance matrix, which is this, or you could show that actually it can also be done with X. I think X transpose X, if I'm not mistaken. You have to, because the features, these things actually are in rows. So if you want to do this, you do X transpose X first, and big matrix X transpose, and gives you the same thing. That's the covariance matrix, and then you divide by M to average things out. So exercise for you guys: can you write this covariance matrix as a product of the original X matrix somehow with itself, and show that indeed the two are the same? But anyways, once you do that, whether you want to do it through the sum or that matrix, you run it through a singular value decomposition, your favorite MATLAB, Python, whatever you want to do. You get your U vector. You will actually also need S. Well, I'll show you in a second. But you get your U vector. You pick based on the S values which ones you want to pick, and then you do the projection. You're done. And that's now you're in a new lower dimensional space. Whatever you want to do with it, look for patterns, look for whatever. It's up to you. How do I go back and reconstruct things? In communication systems, we do this often. We have images that we want to transmit. We have, voice that we want to transmit. We reduce things, and then sometimes we want to reconstruct things back. So if you want to reconstruct things back, guess what you do? What is something that I multiply here to give me X? I want the inverse of UT. What's the inverse of U? Or UT? What's the inverse of UT? U itself. U itself, right? So U transpose is equal to identity because they're orthonormal. So if I take U itself, multiply it by this, I'm going to get X back. So all I have to do, if I want to recover Z, if I want to recover X, I multiply by U. The U reduced. Okay? And it will be, this should be, my x, not z. I'll also fix this later. Okay, now choosing the number of components. How do I choose those number of components? So here we have a simple example. If I have 2D, the only choice I have to reduce it is 1D. Choose one vector. But if I have, like with natural language processing and text, I have 100,000, vector. What should be the new dimensional space? How do I pick it? How do I find it? Well, it's all back to information, right, in a way, intuitively. So the question is, as I reduce the space, am I losing anything or not losing anything? If I have this two-dimensional space and I project everything on one line, do I lose information or don't lose information? I do. If this is very squeezed, all the way that it squishes the line, there's no loss of information. But in general, each one of these U axes has some information in it. The first one has the most, the next one has the less, and so on. But any one of them has information, supposedly, right? So the way you decide, actually, is basically pick as many as you want under a certain threshold. So if I want to, one way of thinking about it, if I go back, there's two ways of thinking about it. From the initial formulation where I want to minimize the error between the x and their projection, if I choose those approximation to be based on the k vector, I want the x relative to the norm of the x squared, the standard deviation variance, to be less than 0.01, I could just simply start by saying, can I do with one vector and get, if everything is squished on that one line, I'm actually going to get zero error. But if not, then, I will try one vector, see if that works. If not, I'll try two. If not, three. If not, four. If not, I may end up trying them all if it's not satisfying. Then I'll say, oh, sorry, I cannot do any reduction. Okay, so that's one way of looking at this. And notice what they say. This is keeping 99% of the variance. So the alternative way is thinking about the eigenvalues, so which is actually a lot easier. So the alternative way is you take the sum of the, and actually it can be shown that this is related to that equation. Again, I'm going to skip this for now, but you can look at the eigenvalues and make sure if I take the first one, is this capturing the variations I want? Is it capturing most of it? And by taking this sum up to k divided by the total sum of eigenvalues in the covariance, remember this is reflecting covariance, so variance in the data. So if I take the first one, does it capture 99% of it? If not, take two of them. If not, three of them. If not, four of them, up until you find that you've gotten 99%. And then you stop. Obviously, this is much faster, right? I mean, all I have to do once I have the S values, I can check this very quickly. This one requires me to do the projection every time, all the reduction, compute, and so on. So this is very expensive computation. This is much faster. Okay? Finally, do I still have time? عندي 1 minute. مين قال no? وفي قلة ترى. So finally, PCA with supervised learning. Can I use PCA? I'll ask the question, maybe talk a little and stop. Can I use PCA for supervised learning and how? Can you give me an example? Let's say I have the example of house information. I have 1,000 information. I want to do a regression model. I can do a regression model in the original space based on the original x values or in the new space, right? Yes. So PCA can be used in conjunction with supervised as long as you keep the labels. When you do the PCA, you're not looking at the labels. That's true. But then you could project them into a lower dimensional space and then work in that lower dimensional space. For whatever reason that we'll talk about next time. And we'll talk also about sometimes where it's not a good idea to do this, okay? And that will be kind of like the end of this. So next time, I'll continue from here. I'll talk about other ways of doing feature reduction, and then maybe we'll use information there, actually, entropy, to pick that, and then we'll continue.